This video will cover reaction stoichiometry. Please read the OER textbook chapter section 7.2 for more detail. The online homework associated with this to help you practice more of this concept is 7.2. So pretty much in the previous video, we learned how to write chemical equation and also how to balance the chemical equation. So in this chapter, we are going to use those balanced chemical equation to help us do some calculation, which is going to involve with the reaction stoichiometry, which is the relationship between reactant and the product. Let's take a look at example on page 131. Okay, so pretty much what we're gonna focus on is why the balanced chemical equation is important, right? Like why do I focus on the previous video, right, before we actually get into this? The reason for that is because the coefficient in front of those molecule in the chemical balance equation can be used as the conversion factor, which means that each of these will tell you about how many molecule for each of those that need to react in order to produce the desired product, right? Or we can look at as number of mole as well, how many mole of each of these, right, that require in a chemical reaction, right? So pretty much that's what we are going to take a look at. Okay, so if you're looking at the number of mole, okay, between methane and oxygen, you will see that the ratio or the coefficient between these two will tell us the ratio that is required for this reaction. Okay, so this is the same reaction that we see earlier when we in the previous video 7.1. Okay, so pretty much we see that for this reaction to happen, it's require 1 mole of methane per 2 mole of oxygen, right? So that's what the ratio tell us. Again, these ratio need to come from the balanced chemical equation. You can look at these to compare between methane and carbon dioxide as well, right? It would be 1 to 1. Or you can do methane and water as well, would be 1 to 2, right? So pretty much you can compare reactant with reactant or reactant with the product in any fashion you want, as long as the coefficient are from the balanced chemical equation. Okay, so you also can compare between mole of oxygen and carbon dioxide as well, right? So it would be 2 to 1, or oxygen and water, or carbon dioxide and water, right, between the two reactant. You can do that as well. So note that these conversion factor that we have can flip depend on what unit you want to cancel. If you want to get rid of oxygen, then the mole of oxygen need to be on the bottom, right? If you want to get rid of water, then the mole of water will need to be on the bottom. Okay, so again, so this can be flipped, and this ratio that you see between each of those molecules within the balanced chemical equation, this is what we call stoichiometric ratio. Okay, so pretty much the ratio that shows the relationship between each of those species within the balanced chemical equations. Okay, so why is this important? Okay, so I'm going to recall from what we already learned in chapter 5.4. Okay, so chapter 5.4, we learn about the importance of chemical formula, which tell us about the ratio between, let's say, if you have compound A and B, right? The X and Y would tell you about the ratio between A and B, how many A and how many B per this one molecule, right? So pretty much that's what we focus on. And in chapter 5.4, you learn the conversion of that. For example, if you know grams of the molecule A and B, you should be able to use molar mass to convert back and forth between grams and mole, right? And if you know mole of A and B, you also can convert that using Avogadro's number to get the number of molecule as well. And what we learned in chapter 5.4 is that if you're looking at A or B, right? If you want to look at each of those type of atom within the molecule, you can use the ratio within the chemical formula, which is X and Y here. This X and Y ratio will allow you to go between the molecule to mole of each of those atom with element within the molecule, right? If you know this ratio, you can either go from mole of molecule AB to mole of just A or B, right, by using that chemical formula. And once you know more of A and B, right, you can either use the molar mass of each of those elements to get into grams, right? And you also, if you know more, you can also get the number of atom as well. So again, the difference between molecule and atom is that molecules, right, is composed of several atoms, right? So the atom A and B, those are talking about just specific element within the molecule. Okay, so that's what we learned in 5.4. This chapter is just add more layer to that. Instead of focusing on just one molecule, we are actually going to look at as a chemical equation, right? So how many of each of these molecules we require in order to for that particular reaction to take place, right? So pretty much that's what we are looking at. So the concept's still going to be the same, right? So pretty much if you're looking at molecule A and B, right? So you can use the molar mass to convert back and forth between grams and mole. And if you know more of A and B, you can also use Avogadro's number to convert to molecule of A and B as well. And according to the chemical formula of A and B, right, you can use that to pretty much convert to the how many atoms of A or B as well. So this part right here is part of 5.4 that I just mentioned. This chapter, it just add one more layer to that. Okay, so instead of go all the way to the atom of the same molecule, we are actually going to go from one molecule to another. So this one, we are still going to use the mole to mole ratio. Okay, so similar to this, right? So this is going to be mole to mole ratio. If you go from mole of something to something else, you need to use mole to mole ratio. Okay, so same thing for this, right? So if you want to go from mole AB to mole of something else, XY in this case, you need to use the ratio. Where is this ratio coming from? It need to come from the balanced chemical equation. So that's why writing balanced chemical equation is really important, because without that, we would not be able to convert from A, B to XY. Okay, so this ratio, or the stoichiometric ratio from the balanced chemical equation, will allow you to go from one molecule to another, right? It can be reactant to reactant, right? Reactant to another reactant, or product to reactant, or product to another product, right? Or reactant to the product, right? So any of those. Okay, so it depends on what you are looking at. Okay, so you are going to have to pick the correct ratio for that associated with each of those molecules. Okay, so now once you know more of XY, then it's going to be the same pattern again, right? If I ask for grams of XY, what do? Well, you're going to use molar mass again, right? So add everything up together, the unit is in grams per mole, right? If I want to know molecule of XY, you are going to do the same thing by using Avogadro's number to convert from mole to molecule. And you can actually find this even further if you want to know atoms X or Y specifically, then you can use the chemical formula ratio of X and Y to help you to achieve that as well. Okay, so that means pretty much this roadmap that you see here is what we refer as stoichiometry roadmap. The most important part of this is going to be the ratio from the balanced chemical equation, because it's allowed you to convert from mole of something to mole of something else. Okay, without that, you will not be able to find out that connection. Okay, so let's take a look at example. Okay, so let's take a look at example 2. So again, so when you see the exam, it's going to be somewhat integrated from the previous knowledge like this, right? So you learn how to write chemical formula before, you learn how to write balanced chemical equation before. Now the next thing is we're going to add more layer to that, which is now we're going to add stoichiometry concept into that. Okay, so in this case we have solid aluminum oxide. Okay, so what is aluminum chemical symbol? It would be Al, right? And because this is metal, this is metal and this is non-metal, therefore you will need to make ionic compound, which is going to be cation and anion combined, right? So aluminum would be 3+ because it's in group 3A or 13, right? So it have 3+. Oxygen, right? Oxygen is in group 16 or 6A, so it would have 2-. So therefore, the chemical formula of this aluminum oxide would be Al2O3, right? Because you need to make this to be neutral. Okay, so solid. Okay, decomposes. Okay, so decomposes too. So decompose mean this is gonna break apart. Okay, so I'm going to break apart to what? To solid aluminum. So it's just gonna be Al. Okay. Oxygen gas would be just O or O2. The answer is going to be O2, right? Because oxygen gas is one of the diatomic molecule. Therefore, in this case, this is going to be your chemical equation. Is this chemical equation good to go? The answer is no, right? Because you need to make sure that the chemical equation need to be balanced in order to use in the calculation, in the stoichiometric calculations. So in this case, you need to balance that, right? So we have 2 aluminum. If you start with 2 aluminum, if I add 2 here, oxygen will still not going to be balanced. That means I can't start with aluminum because it doesn't lead to the productive pathway, right? So in this case, I'm going to start with oxygen. So 3 and 2, right? Common number would be 6, right? So it would be 3 in front of this. So that way 3 times 2 equal to 6. So if you have 6 oxygen here, you need 6 oxygen as well. So you add 2 in front of it. So now you have 4 aluminum. So add 4 to that. So this is the balanced chemical equation. Okay. So the next thing is find out what are the information that's given to you. Is given you the mole. Okay. Mole of what? Mole of aluminum oxide. Okay. So it's mole of this. Okay. So that means in this case, you are going to set up with that given information and go to all the way to what it asks you for, right? Which is it's asking for the mole of aluminum. Okay, so it's asking for more of this. Okay, so this is given. Okay, we know this. Okay, this is what we want to know, right? That's what it asks for. So pretty much what we're gonna do is, if you follow me with this stoichiometric ratio roadmap right here, what's given is given here. Okay, so we're not gonna start all the way to grams because it doesn't give us grams, right? It's give us mole. So you're gonna start right here. Okay, so again, make sure you start where it's given. Okay, so since already given here, you don't need to go back to grams again. It's just waste of your time. So we are going to start from this given mole. So so mole of A and B. So these just represent the 2 different species. And yes, we talk about 2 different species, right? So we talk about this one and this one. There are 2 different molecules. So I'm going to represent this as A, right? And then I'm going to represent this as B. So according to this, okay. So this is what given. We want to find out mole of aluminum. So that means all you need to go to is going to be this, right? Because that's what it asks for. It asks for mole of aluminum. Okay, so that means the only thing we need for this information right here would be the stoichiometric ratio, which is the ratio between these 2. Okay, so how do I set up? So start with the mole that is given. So that way we cancel the unit, right? So this is mole. Make sure that you remind yourself as well, mole of what? Is mole of aluminum oxide. So it's mole of this. Okay, mole of this, since we don't want it, right? Because it doesn't ask for that. It's asking for more of something else. Therefore, in this case, mole of aluminum oxide need to be on the bottom, right? In order for this to, will have to cancel each other out. And mole of aluminum would have to be on the top, right? Now, what are going into here? This is when the ratio will go into, right? So 2 aluminum oxide will go here, 4 aluminum would go here, right? So that would be the ratio. Because in this reaction, every 2 mole of aluminum oxide would decompose into 4 mole of aluminum. That's what it means. Okay, so that means if you cancel the unit, you will see that mole will cancel out, right? So again, this is come from the balance equation, and you are going to have mole of aluminum left as the final answer. So that's going to be your answer. So that means if you have 2 more of this, it's going to decompose to 4 more of this. But if you have less than 2 mole, right, 0.46 mole, then it's going to decompose to only this much of aluminum, right, 0.920 mole. Now let's take a look at the next example. So this one is already giving you the chemical equation. So, and then it's asking you to calculate for the mass in grams of iron. Right? So pretty much this is iron that react with hydrobromic acid that produce iron 2 bromide and hydrogen gas, right? So pretty much what you need to first step, what you need to do is make sure that this is already balanced, right? So if you check this reaction is already balanced, so that's good to go. Once you know that this reaction is already balanced, then you can do all the calculation. Okay, so again, so before starting any calculation, make sure that the chemical equation that is given is already balanced. If it's unbalanced, you will need to balance it because you need to use the balance coefficient in order to do the calculation. Okay, so what it's given us is 1.7 mole of hydrogen gas. Okay, so it's giving us the product in this case. It's asking for the mass of iron reacted. So asking for mass of iron, which is the reactant. So this one is giving you product, asking you the reactant. So again, as I mentioned earlier, it doesn't matter which one you start with, right? It can be given product or with the product, or it can giving you product and reactant, or giving you reactant asking for product. So it can be any of those. So the key thing is you will need to use the balanced chemical equation, stoichiometric ratio, to help you to go from one species to another. Okay, so that's the key part right here. So it doesn't matter which one you start, you just need to use the stoichiometric ratio to help you to convert. Okay, So what you are going to do, I'm going to put this back into the stoichiometric ratio again, and I'm going to call what's given here as A, right? So I'm going to call this hydrogen gas as A, okay, and then iron, solid iron would be B. Okay, so this is asking B. So pretty much what we are going to start is we're going to start right here, right? A, and then we're going to go to B because asking for a different thing. Okay, so given A in mole, so where do we start? Do we start molecule? Do we start grams? Or do we start right here? The answer is we're going to start right here, right? Because that's what given is given at mole. It doesn't given you at grams. If it's given you at grams, then you use molar mass to convert to mole. If it's given you in molecule, then you use Avogadro's number to convert to mole, right? So this is something you already know. These are the skill, my expectation for you, as I already mentioned, this conversion between grams to mole, mole to molecule is really crucial throughout the whole sequence of chemistry. If you are not master in this conversion, you will need to actually practice a lot for that, and also visit me during office hour as well. Okay, so you need to be master in that. Okay, so in this case, it's already giving you mole. Okay, so asking you for grams. So that means grams of what? Is grams of iron, right? Which is part of the B. So gram is right here. So this is what it's asking you for. So therefore, in order to go from here to here, you will need to go through this route, right? So that means you need to somehow convert this mole of A, right? Mole of hydrogen gas to mole of iron, and from mole of iron to grams of iron. That's what it tells us to do. Okay, so what I'm going to start with is I'm going to start with mole of hydrogen gas that is given. Okay, because that's the only number is given in this case. So you are going to need to cancel mole of hydrogen gas because we no longer need that, right? Because eventually you're gonna need to get rid of that in order to get grams of iron. So mole of hydrogen gas, how do we go from here to here? That's when you are going to use mole of iron. Remember, when you have two different species or two different molecules, right? You will need to use stoichiometric ratio to convert between them. So in this case, we are going to use stoichiometric ratio. Even though it's 1-to-1 on the exam, you will still need to include this part. This part contains point associated with it. Even though it's 1-to-1, you still need to show me that the unit will need to cancel out. This is how you convert unit of hydrogen gas to the unit of iron. Okay, so this is come from balance equation again. Even though it's 1-to-1, you still need to include this part. Okay, so mole of hydrogen will cancel out. Now you have mole of iron left. I don't want to know mole of iron. I want to know grams of iron. What do we do? Well, mole to grams, we are using what? Molar mass, right? The molar mass is in unit of grams per mole. So you are going to look up the periodic table for this. Right, so this is just Fe. So you are going to look up the periodic table to get this number. So this number from periodic table would be in unit of grams in every 1 mole of iron. If you cancel out the unit, you will see that grams of iron will be left. So therefore, in this case, 95 grams of iron would be the answer. So what it means is that if you have 95 grams of iron, right, if you start right here, once it reacts with hydrobromic acid, it's going to produce 1.7 mole of hydrogen gas. That's what it tells us. If you have this amount, this is the amount that is going to be produced for hydrogen gas. Okay. All right, so let's take a look at 3B. Okay, so 3B, if 25 grams of hydrobromic acid are used, then how many mole of iron bromide, right, would form? Okay, so again, this one, if you is given, you need to find out what is given. It's given as hydrobromic acid, right, and it's asking for iron bromide. So again, you can use stoichiometric ratio again, right, to convert from mole of something to mole of something else. We need to go through this part. Okay, but in this case, it's giving you to start with grams. Okay, so it start with grams. So therefore, we're gonna start with grams. Grams asking for mole. So we're going to stop right here. So it depends on what the question asks you. Okay, so you're going to stop where it's asking you. Okay, so we're going to stop here. We're not going to go all the way to grams. Some problem, you might have to go from grams all the way to grams. It just depends on what it asks you. Okay, so you need to watch out for the questions. Okay, so in this case, start with grams of HBr. Remember, everything connected by mole to mole ratio, right? So all of these ratio in front of this is mole to mole ratio. So that means you have to always convert grams or molecule to mole first before you can convert from one species to another. Okay, so in this case, we are going to have to cancel grams of hydrobromic acid. How do you convert from grams to mole? Well, we're going to use molar mass, right, which is in grams per mole. How do you find out that? Well, it's going to come from periodic table. You're going to add mass of these two together. That would be the mass, right? Unit would be in grams of every 1 mole of hydrobromic acid. Okay, so grams cancel out, you're going to have more of hydrobromic acid. Now you have more hydrobromic acid, we're going to cancel that. Okay, so, and then we're going to go to more of FeBr2, right? Because you already get into more of HBr. The next thing is to go from more of the reactant to more of the product by using the stoichiometric ratio here. And the ratio would be 2 to 1 in this case, right? 2 more of HBr is going to provide 1 more of iron to bromide. Okay, so now, do I need to go further to grams? The answer is no, because it's asking for moles. So you stop right here. This is moles, right? Not molecules, not grams, so you stop right here. So therefore, if you cancel all the units, you are going to get 0.145 mole of iron to bromide, which indicate that this reaction, if you have 0.154 mole of iron bromide, it's going to come from, right, 25 grams of hydrobromic acid that react with the iron. That's what it tells us. Okay. All right, next one. So in this case, I would like you to pause the video and complete this example for yourself. Once you finish, resume the video again. Okay, so I would like you to really practice this. Okay, so let's pause the video now and then resume the video when you finish. Now let's check your work against mine. Okay, so pretty much it's giving us the chemical equation. Okay, so asking us to calculate involved with grams and grams here. So in this case, again, before we start doing any calculation, remember you need to make sure that this chemical equation is balanced, right? So pretty much if you check this is already balanced, right? Because there are coefficient in front of this, so this is already balanced. So once we know that the chemical equation is balanced, then we can start working on the calculations. Okay, so the calculation is giving us the N2O4. Okay, so it's this one right here, dinitrogen tetrahydride. Okay, which is in grams. So we're gonna start in grams right here, asking for grams of dinitrogen tetraoxide, right, which is another reactant. So that means in this case we're gonna go from grams to another grams. Okay, so grams all the way to grams. Okay, so what do we do? Well, that means we need to convert from grams to mole first, then mole to mole ratio, right, and then mole of N2O4 to grams of N2O4. Okay, so pretty much if you check your work, this is how I set it up. Okay, so let's check your work. So again, start with what is given, right? Mole of dinitrogen tetrahydride, right? And convert that to mole by using its molar mass. Add all of this together, you're gonna get grams. So this is come from periodic table, okay? And then once you get mole of dinitrogen tetrahydride, then you're gonna use the mole ratio between these two to convert to mole of dinitrogen tetraoxide, right? And because it's asking you for grams, so we're gonna go one more step further. So which is converting mole of dinitrogen tetraoxide into grams of dinitrogen tetraoxide. Okay, so by using its molar mass, by adding all of this up together, looking on the periodic table and add them up together. Okay, so once you do that, you will see that all the units will cancel each other out, and your answer should come out equal to 21.5 grams of dinitrogen tetraoxide, which indicate that, well, if you want these two to react completely, if you have 15 grams of dinitrogen tetrahydride, it's going to require 21.5 grams of dinitrogen tetraoxide. That's what it tells us. Okay, so again, pretty much this part right here, these two parts is coming from periodic table. Okay, so these two parts, you will need to add them. And this part right here, this is coming from the stoichiometric ratio, which is the ratio in the balanced chemical equation. Okay, so mole to mole is always come from this equation right here. It have to be balanced though. Okay, grams to mole come from when you add everything up together from the periodic table. Okay, so pretty much this lecture video cover the stoichiometric roadmap. So far what you see is you see conversion between mole to mole, right? Grams to mole, grams to mole to mole to grams. I have not covered the molecule yet, but it's the same idea. Okay, so on Newton homework, you are going to see all of this. Okay, so Newton homework might give you the molecule as well, but pretty much it's going to be the same. If you are given molecule, all you have to do is using Avogadro's number to fit into mole. As long as you get into mole, you can go from mole of one thing to mole of another molecules. Okay, so again, Newton homework, chapter 7.2 will help you understand this better. Okay, so start working on the online homework.